Okay, so today we will start with another topic, in entirely new topic, which is kinematics of a rigid body. So say for example, you have a rigid body here. So the first question which arises is, what is a rigid body? So rigid body is a special case of system of particles. So every rigid body is made up of individual particles. So it is rigid body. So it is a system of particles. Okay, and it contains infinite number of particles. So it has infinite number of particles in it generally. So when you apply everything that we have studied in a system of particles to a rigid body, your summations that we were performing will be replaced by integrals. And the third thing, which is the most important thing about a rigid body, is that if you have say 2 points on a rigid body, A and B, any 2 points, then if the position of A is RA and position of B is RB, then this vector, which is denoted by RB slash A. So what is RB slash A? It is relative position of B with respect to point A, and it is given by RB minus RA. Now for a rigid body, the most important defining characteristic is that magnitude of this vector RBA is constant. RB slash A is constant. Let me take a unit vector EBA along this vector RBA. Then your RBA can be written as RBA and into magnitude into its direction EBA. So I can expand RBA into RB minus RA. Is equal to RBA EBA. Now if I take derivative of both sides, then I will get VB minus VA, which is also written as velocity of B with respect to A, is equal to time derivative of RB A into EB A. Now for a rigid body, this is constant. So we take that out and write EB A over dt. Now you know derivative of a unit vector, how to calculate that. So I will simply use that formula which I have used several times in the class. So VB, just a little rearrangement, taking VA to the right hand side, VB is equal to VA plus RB A omega cross EBA, where omega we will denote by omega A because it is unit vector which is rotating about A. So rotation is about A, so I'll write omega A. Now this scalar I can bring inside to write VA plus omega A cross RBA EBA, and this is nothing but vector RBA. So this is the most general relation for velocity between 2 points, relation between velocity of 2 points on a rigid body. VB is equal to VA plus omega A cross RBA. So this is very important relation, and this is a very general relation between 2 points on a rigid body. Velocity of 2 points on a rigid body for any general motion of the rigid body. To understand this relation better, we will take a number of specific cases. So in your book, general motion of a rigid body has been divided into 5 cases. So the first case is translation. So what happens in translation is there is no rotation. There is no rotation omega A. So in translation, VB omega A will be 0 and VB will be equal to VA. So velocity of every point on a body will be same. So if you have a body here, it has this point A and it has this point B. So in translation, so for translation there is no rotation of this RBA vector. So this VA will be equal to VB and the body will move. So and this line joining A and B, what kind of motion it will experience? It will just move parallelly. So if this is VA, so if this moves like this, then the trajectory of point B will be parallel to the trajectory of point A, and in final position AB will be parallel to its initial position. So if this is AB and this is A prime, B prime, so these will be parallel. and these trajectories are parallel. So these lines will be parallel, the line joining AB, and these trajectories will be parallel. Why? Because there is no rotation of vector RAB. Now the second case is rotation about a point. So starting from your general relation VB is equal to VA plus omega A cross R B slash A. If A is fixed, that is, suppose this is your rigid body and there is a point which is fixed, so it may undergo some motion, but this A will not change its position. So in that case, VA will be 0 and your relation will be VB, velocity of any point with respect to the fixed point, will be rotation with respect to this fixed point cross position of B with respect to A. Now there is another specialization, which is rotation about a fixed axis. So suppose that you have a body and now it is rotating not just about a fixed point but about an axis. So for example, it has this axis and your rotation will be about this axis only. So your omega has a fixed direction now. So here omega was changing its direction in the previous case. So omega at one instant it could be like this, or at another instant it could be like this. But here omega, though it can change its value, it will be always omega k if k is the direction of this axis. Then in this case we can write VB is equal to VA plus omega k cross R B slash A. Now if A is any point on this axis, VA, velocity of A will be 0, VA is 0 for any point A on the axis. So VA will be 0 if it is any point on the axis. So velocity of point B will be omega cross R B A. If you put your origin at A, then this will be simply RB because RA will be 0. If I want to find acceleration of any point on the body, then I can differentiate this. So what I will get is omega dot k cross r b a plus omega k cross v b a. Now you know that VBA is nothing but VB minus VA. So this VBA is VB minus VA, and VA is 0. So this is equal to VB, which is omega cross RB slash A. So this expression for acceleration of a body undergoing rotation about a fixed axis is given as this. So omega dot can be denoted by alpha, angular acceleration. So angular acceleration cross RBA plus omega k cross omega k cross RB A. So if A is at origin, I can write this as AB is equal to alpha k cross RB plus, rather minus, if you do it R cross omega k. So this comes out to be minus omega square. This comes out to be along RB just by performing cross product. So this is tangential acceleration, this is centripetal acceleration. You are also familiar with formula for angular motion, for a uniformly accelerated motion. So those formulae you can use. I will just write them here. So omega is equal to omega naught plus alpha t, and so they come directly from angular motion of a particle. Theta is equal to theta naught plus omega naught t plus half alpha t square, and finally omega square is equal to omega naught square plus twice alpha theta minus theta naught. This is for uniform angular acceleration. That is alpha is equal to constant. Now there is another special case, which is plane motion of a rigid body. So this will be your case number 4, and 5th will be the general case, which we will not be studying in this unit. General plane motion. This is the most important one from examination point of view. So what is general plane motion? So in general plane motion, as the name suggests, your body will move in a fixed plane, right? So it can rotate, it can translate, it can do a combination of both, but its rotation will always be perpendicular to the plane. So for a general plane motion, what you can write is that if k is direction coming out of the plane, then for general plane motion, Vb, starting from the general relation, Vb is equal to Va plus omega A cross Rb A. Now for general plane motion, your omega will always be omega k. This is different from rotation about a fixed axis, because Va is not 0 here. But like rotation about a fixed axis, rotation is given like this. So we will write Vb is equal to Va plus omega A k cross Rb A. If I want to write velocity of A with respect to B, then I can write a similar relation like this, just interchanging A and B. Now if I add these equations, so adding these equations, Va, Vb and everything will cancel out. What will remain is omega A k cross RBA slash A plus omega B k cross R A B is equal to 0. Now this RAB is negative of RBA by definition. So this equation becomes omega A minus omega B k cross RBA is equal to 0. So this proves that omega A is equal to omega B. Now what does this relation mean? So this relation means this. Let us consider a case that, say you have a body, a rigid body, which is like this. So this is its initial position and this is AB. Now you have its final position like this. So in general, AB. Now this relation VB is equal to VA plus omega A cross RBA. This relation basically means that motion of body of point B can be decomposed into a translation with the velocity of point A and a rotation about A. So from this initial to final, what will happen is that if you choose A as your reference point, so VB, so this final position will be obtained in two ways. In one way, so this is velocity of A and this is velocity of B. So one way will be that this whole thing translates with the velocity of a. So if that thing happens, then what will happen is that it will achieve a state like this. Sorry. So a will reach, so velocity of a we are using for translation, so a will reach its final position, but b will not be its final position. To bring b to its final position, we will have to rotate it by an angle. We have to rotate about theta a, about a. Now there is another situation, that if we translate the body first about point b, so if I translate this with the velocity of b, so b will reach its final position, but a will not be in its final position, and a will come to its final position after a rotation with b, about b. Now this relation says that this rotation about a or about b is same for plane motion. In 3D motion this might not be same, but in plane motion you only have one rotation. Yeah. So no matter which point of reference you choose, rotation will always be about same position, will always have angular velocity will be same irrespective of the point you choose for reference, a or b. Now in problems, the most important relation that you have to use is this: vb is equal to va plus omega k cross r b a. So this is just omega. Even if you write about another point, say for example cd, vc is equal to vd, then again this rotation will be same for plane motion. So this omega is always same for plane motion. Another concept in plane motion which is interesting is instantaneous center. So instantaneous center is a point at which velocity, so instantaneous center I is the point vi at which velocity is 0 at an instant at some time t. So in general there are different, or rather location of I changes with time, but still you can use it to find velocity using this vb is equal to vi plus omega k cross rb I, and this is 0 at an instant. So for another instant it could be different. So for example, in case of a wheel, at each instant velocity of the wheel at the contact point is 0, but as the wheel moves this contact point changes, but at every time instant you can use the current point which is in contact to find velocity. So if this is 2r, so this velocity is, So this is pure rotation about this point, instantaneous center. So at any instant you can write velocity as, this will be 2 r omega, this will be, sorry, it will be half, this will be r omega, and this will be 0, vi is equal to 0. Geometrically this can be seen like this, that suppose there is a body and you are given velocity at 2 points. So this is va, this is vb. Then if you draw perpendiculars, let me draw vb like this, to the velocity vector. So at any instant they will intersect at a point which is instantaneous center I. It can be inside the body or can be outside as well. Another thing is that if the velocity vectors are parallel, so as in the case of wheel example, then you can draw a triangle to find instantaneous center. So this va, so if this is ra, this is rb, then this va will be omega ra, this will be omega rb, and same here, this is a, this is b, so this is omega ra, omega rb. Okay, so let me just highlight the main thing which is required for solving problems, and that thing is, for plane motion you have to use this relation omega vb is equal to va plus omega k cross r b slash a. This is a vector equation, so in some cases you might be given direction of velocity b or magnitude of v or components of b. You could also be given magnitude, direction or components of a. So you have to expand this into two equations. So expand this into x equation and y equation and find whatever is required, omega or vb or va, whatever is required.